All right, we've reached the top of the hour here, so we're going to go ahead and get started. For those of you that have tuned in with us before, just a couple of housekeeping notes. We've got two guest presenters today, Graham Madison from Camstrup and David Wills from Census. I'm going to be talking about advanced metering infrastructure. If you have questions for them as they're giving their presentations, please enter those into the Q&A window. You can find that by hovering over the Zoom menu bar and finding that Q&A spot. That way we can be sure to ask your questions at the end of the presentation during our Q&A session. If you do put your questions in the chat, I'm going to try to keep an eye on it as we go along, but they may get missed. So we do recommend that you use that Q&A window. Just a little bit about CDAC and who we are here. We are an applied research program here at the University of Illinois with the goal of reducing the energy footprint of Illinois and beyond. So we assist communities and buildings in achieving energy efficiency, saving money, and becoming more sustainable. We are housed at the University of Illinois in Urbana-Champaign, but we do reach throughout the entire state. As part of this public water infrastructure program, we partner with the Illinois Sustainable Technology Center, who has a similar mission to us in promoting sustainability through providing technical assistance, outreach and training, and applied research programs. The Illinois EPA Office of Energy is a sponsor for this program. We thank them for their support and for helping us to bring this training presentation to you today. We do have an upcoming field day on May 15th. We're going to be visiting an algae wheel process near Gardner, Illinois. So if you haven't yet, please do find the registration for that and join us out there to take a look at some interesting green technologies that wastewater treatment plants can employ. We'll be starting off the day with a workshop at the Village Hall in Gardner, and then we'll be going out to an algae wheel treatment process at the Bookwalter Woods Mobile Home Park. So you actually see that process in person. A little bit more about our program here. We are partnered with the Illinois EPA Office of Energy to provide this public water infrastructure energy assessment program. Through the program, we offer no-cost energy assessments and technical assistance to publicly owned and operated wastewater and water treatment facilities throughout the state of Illinois. There are a limited number of slots left this program year, so if you haven't signed up yet, please do. We can help you through that application process and get all the information we need turned in so that we can get your assessment taken care of. As part of our assessment process, we offer a comprehensive report listing the cost of upgrades, estimated payback periods, energy savings opportunities. We try to touch on non-energy benefits of upgrades as well. And our program also offers continuing education events such as today's webinar. So why might you want to complete an energy assessment? If you have an older system or you've never had an assessment before, we can help you identify missed opportunities, plan for future capital improvements, uncover new possibilities for your existing plant. And we know a lot of operators already have ideas for ways they want to improve, and we can provide that third-party support, help you calculate potential savings and economics so that you can help drive those projects forward. If you've got a brand new facility or you've recently upgraded, there's always more ways to improve facilities. There's new technologies that are coming out. Budgets are tight, so projects often leave things to the side for future projects. They can't afford to do everything and hit their entire wish list all at once. So we can help identify and build out a future plan for future improvements as well. But there's always an opportunity for repairs or upgrades, and we can also connect you to funding opportunities to help support those. To access our program, you can apply at our website, smartenergy.illinois.edu/water. You just have to be located within the state of Illinois and be publicly owned. You got to allow us to come out to your site so that we can take pictures, document conditions, gather data and information that we need to develop your report. You have to be willing to share facility information with us, such as your utility bills and operating reports or discharge monitoring reports. And we do share our final assessment report with the Office of Energy so that they can track the effectiveness of the infrastructure program. As far as data collection goes, this is probably the the most difficult step in the process for plants and operators. So we do have to collect up to 2 years of utility data and your monthly operating reports or discharge monitoring reports. And we do know most plant operators don't have direct access to those bills. They're handled by someone at the city office, a city clerk, someone like that pays those bills and has access to those. So we can help if we need to contact that city clerk directly or pick those things up on site. We'll work with you to gather that data that we need to make that as painless as possible. And then we'll come out and do the site visit. It's usually a couple of hours of us on site taking pictures, asking questions, going through your process. Then we'll bring that back to the office and start developing your report, which takes us about 60 days to develop and get back to you. But on to today's presentation. As I mentioned before, we have speaking first, Dave Wills. He's a manager of technical solutions for the Midwest region with Sensus, a Xylem brand, with 23 years of experience in the utility AMI sector. And then speaking second, we'll have Graham Madison from Camstrup. He's a solution manager with 16 years of experience in the water industry and 10 years in acoustic leak detection. And he's been with Camstrup for the past year as a solutions manager. So at this point, I will turn it over to David.
Hey, let's see. So are we still sharing here? Do you see my?
You'll need to reshare your screen.
All right, got it. Yep. All right. How about now?
Perfect. That.
Okay. Great. All right. Good morning. Thank you for joining. And today we're going to talk about the smart water utility with AMI. And let's just get it going. So here's an agenda. We'll do an overview of metering history to AMI. Then we'll talk about how AMI grows beyond just a meter read. We'll have a case study, some customer information. We'll talk about some metering and sensors, pressure planning, and real case scenarios for pressure management and leaks, and then just a quick summary. So the way we look at, the smart water cycle, as we'll call it, right? We know that, we have surface water that, comes in, we know there's sourced groundwater, and we just kind of draw up what the whole system, looks like. And we have basically 3 goals that we're looking to try to accomplish, right? We want to make the job easier for the utilities. That's billing, customer service, field engineering, finance, utility manager. Then we look to help operations. How can we make operations more effective, right? Is that with treatment? Is it with help treating? Is it with help transporting? Sustainability, and then try to make sure to help in the financial realm of the utility as well. And then the final thing that we really look to do is long lasting, right? We're looking for systems to be upgradable, expandable, and certainly reliable. And as we know, more utilities are taking on Lake Michigan water, such as cities in Illinois and Wisconsin, including my home city. And it will become more important to achieve, these goals as we move forward. Okay. All right. So how did we get to where we're at? Well, it basically started with metering in the 1870s, right? Sorry. 18, sorry, it's jumping. There we go. 1870s, we started with metering. At that point, all they did is they started laying out the infrastructure. They said, hey, we're pumping water, we're getting water residents, we're going to have to start calculating and metering it. So from the 1870s to 1984, though the technology advanced, the data processing was still based on manual reads. In 1984, got a little easier with walk-by technology, which improved the speed, the accuracy of the meter reading. And then in 1993, come up with the drive-by solution, which further improved the accuracy to form what we have, AMR today. As we looked into the 2000s, we started looking at, widespread adoption of advanced metering infrastructure. It starts to look at a fixed base meter reading solution versus looking at, the previous drive-by walk-by. What it led to is the big one was, you had reduced truck rolls, right? And reduced employee time to read meters. Missed an estimated reads now were much lower in that, and then had bill inefficiencies that allowed us to do, more frequent, reads that, could help reduce customers, sticker shock. And the big thing was it just gave an opportunity for greater customer engagement for more accurate and more frequent data on that side. Now, today, right, smart utility is, it's unlocking a high value, and that becomes with what meters can do these days, right? At residentials, we can now do pressure, temperature, we can, remote disconnect, so we have control of the meter, we can send firmware down to the meter. There's lots of advances that continue to happen in metering, on the residential side every day. And then we have smart monitoring that we put, across the network, right? Where the distribution, the transportation, throughout the network can be measured, it can be reported on. So it's definitely a big advantage, on that. Okay, as we look at a case study here, we'll take Walla Walla, Washington. For us, it was one of the earlier, adopters of it. Now, we do have a few utilities, even in Illinois now, that are adopting this same methodology and system that Walla Walla went with. Walla Walla's background, they're a population of about 33,000 with 11,000 services, have a resilient water supply of 24 million gallons daily capacity, 90% of which comes from surface water, and then they have 10% of groundwater, as well as an aquifer storage and recovery at what we call an ASR for, those peak demands and emergencies. One of the bigger things for them is they realized, hey, we have an aging water distribution system. And with that, what are some of the things that we may need to start looking at that will help us, manage, monitor, and keep track of? Now, Walla Walla has large elevation changes across their system, right? So that requires that, they look at 4 pressure zones with 29 of the, pressure reducing valves that, are in their system as well. On their AMI side, they completed their deployment in 2018. All 11,000 service connections were changed out to smart meters. 99.6% system read success across commercial, industrial, as well as residential. And the immediate outcomes started becoming apparent for them, right? Customer side leak detection. So now they were able to detect when customers may have, leaks going on into their residence. It reduced the winter estimates, and overall it increased the accuracy. So you can see to the right, that's kind of the layout of how their system was deployed. And you can see the other thing is all the different lines and pipe sizes that they have throughout their system as well. Okay, the technology utilized was a smart water meter, and this one allowed the monitoring of parameters in pressure, temperature, and consumption. So now they have this spread out through their utility. And it also gave them capability of remote valve functionality, which open, can be closed, and can be reduced. So there again, the ability to be able to trickle water can help customers, with maybe they're getting in to pay their bills, or if you have, people that are move in, move out, and you need to shut off the water, you have that capability to do it as well. There's a side view of the meter here that shows the valve in the white there inside the meter. Okay, another technology, which was a big one for them, was a smart gateway sensor. What this sensor does is it has 2 analog inputs, a 4 to 20 milliamp, 2 digital inputs, which would allow you to be able, if you got, doors closing on, say, water treatment plants, or you've got garage doors opening, it could allow that to be sent up to the network as well. It is a battery powered device, and it is rated class 1 Div 2. And works outdoors. So they were deploying these along with the meters, and they already had our commercial meter, C&I meter, which has test ports to do pressure and temperature as well. So these sensors are all different types, right? They can monitor water quality, They can monitor movement of water, which we're discussing in pressure and flow. They can do, tank levels. And also you have the ability to monitor for leaks and using acoustic devices as well as hydrophone devices. There are others that can be sampled as well. I've not yet seen one for wind deployed yet, but I have seen chemical feeds done and certainly cathodic protection. And on the wastewater stormwater side, you can measure the dissolved oxygen, the hydrogen sulfide, the level, as well as what the grinder pump may be, pushing out, and any vacuum valves as well as flow. So it allows the utility lots of flexibility in using or utilizing an AMI system that can help them. So how did it start? Well, the way it started was with a pressure monitoring plan, and that's where you come in and look at where all the devices are placed that they have. And then what you do is you address it and start coming up with the monitoring locations that place pressure sensors at the highest and lowest elevation in each one of their 4 zones. All their 6-inch and larger meters were fitted with pressure devices, and they put pressure or monitoring devices on their upstream, downstream of each, pressure reducing valve and pressure sustaining valve, as well as the booster pump station. And they added additional sensors to make sure they had the desired vertical spacing and minor elevation resolution, as well as horizontal spacing, which was across the water network miles, meaning the pipes. Okay, how did they see it once it all comes together? So once it all kind of comes together, you can see that there's a plan that shows where all the sensors are at, along with a heat map to the left. That allows us to do, monitor PSI. There's other factors you can put in that you wanted to monitor. So any sensor that you've got in there has a capability to be monitored. This one just happens to be the pressure values. And you can see that they've selected certain sensors that they want to look at. And there's a graph that's formed at the bottom that lets them know what these pressures are doing, what the fluctuations may be, and any differentials they may have. Basically, it just increases the system visibility, to be more proactive in the distribution. Okay, here's a real case of, a construction project. In this particular case, they had a large meter main replacement that they were doing. They installed a temporary bypass line, and they wanted to ensure that pressure in the area was adequate during that construction project. The meters and sensors were already deployed. And so what they did is they enabled, which is circled in red, a device, their device grouping, which allowed them to uniquely monitor this project. So they could, every time they needed to, they could look at it, or they could get alerts if the pressure, went too high or dropped below what their values were set at. So it gave them a good view of, being able to monitor, what's going on when they start to make changes to the distribution system. Another case is where they ran into a low pressure area. So what happened is a customer called in complaining of low pressure. And the utility, confirmed that, hey, there's 40 PSI in this area. So they sent out a guy to go and take a look. But when the guy comes, he comes at, say 2 o'clock, which is 14. Sorry. Hitting too many buttons here. Okay. 14 hour, 2 o'clock. So he would have seen the pressures around 70. So he would have said, well, it's okay here. Well, what they found was that by being able to look at the pressure profile, they could go to the complete timeline and see that, yeah, at 5 o'clock it was dropping. So as you see, they worked with customers in the utility who were irrigating during the morning hours, had them adjust their schedules, and then adjusted a pressure sustaining valve that helped keep, the levels above 45. So another great thing with being able to monitor pressure. Here's one that utilities sometimes would probably see as, it shouldn't have huge impacts, but in this case, it did. Here's the timing where they're filling a reservoir. And we can see that right here, they are filling up their 10 million gallon reservoir. And they've got a 16-inch main tied to it. And look what happens. The pressure drops, right? And so with that, they go and say, hey, we got to make some adjustments. So what they did is they spread out the filling time so that they didn't have to, pull on the system to fill it up so fast. They had more time to do it in this case. And it's just, it's just a result of having much better monitoring and being able to see from these various, tanks and what impact it has on their pressure, as well as the water treatment plant that sits upstream. Okay, and then here is leak control. This is where you've got a PRV. It's really starting to go bad. You can see it on the left. It's up, down, and then now all of a sudden it goes into a closed position, right? Well, the utility was able to, see this on the pressure profile and say, oh, yep, we've got a problem here. We need to go out. We need to get this PRV corrected so we can take care of it. The interesting thing here is their SCADA system did not even pick up this anomaly, this situation. It didn't see it. It was caught really by the app here. All right, and then let's talk about leak control real quick. So we know that we have basically background leakage, unreported leakage, as well as reported leakage. In this particular case, this comes out of the AWWA M36, and every one of these tools that are up there talk about pressure stabilization and pressure reduction. So it becomes a common monitoring tool to monitoring helps us with this phase of it. All right. And then what does this all mean? This is really a slide that I kind of like, right? Because what it tells us is it says your losses throughout the entire water system, can be certainly a result of how much pressure is in the system. And the way it's, calculated out now is that it looked at it and said that if you reduced pressure, by 2 psi, what you would find is that 0.79 gallons per service connection per psi would drop, and this comes out of the EPA sourced with the Water Research Foundation. And we see in the chart that before pressure management, reported leaks and bursts are certainly high up there, and you have that background leakage going on through the system. Now, when you make the adjustments, now you can bring that, that unreported leakage is down, as well as the background leakage. And this helps, again, with the utilities being able to, reduce loss. Now, not all utilities can look to do that, right? Because lowering the pressure, it equals lower background, leakage and reduced chance of burst, but also, along with reducing the risk of, and extending the life, utilities are usually hesitant to be able to reduce pressure uniformly across the system. And the reason is because, they worry about the effects of, what's this going to do could be negative, down the lines. So what this pressure monitoring would allow them to do is be able to, get through it with, no issues. All right, and then acoustic monitoring. This is where we use loggers to, find out across the lines. You can put these on your gate valves, PRVs, different lines along the system, and it just listens. And what it's looking for is it's looking for a constant sound over time that allows us to be able to detect the leak. And you can see that in this particular case, as a leak starts to happen, we see that, the spread a low spread, which is our line in the, blue. When it goes low, that's a high probability and a high confidence that a leak has occurred in the system. So it's one of the things also that works via the AMI system to help, utilities. And we do certainly have some of these deployed, in Illinois as well. Finally, just in my summary, we're always looking to expand, the traditional AMI networks to give these applications, right? And it's hourly consumption, that they may want from the residential meters. It could be the accuracy, the pressure and the temps that are on the commercial side of things. And it could be other sensors that are put in place, but it all kind of comes together through, a network management package, special smart applications and data analytics, and then if needed or desired, customer portal where the customer can be able to see their side of it. And for me, that is it. Just want to thank everyone for keeping the water flowing. All right.
Well, thank you, Dave. So we'll turn it over to Graham now.
All right, let me get the screen share going.
All right, you're all set.
So we're able to see the presentation all right before we get going?
Yes.
So my name is Graham Madison. I'm a solution manager with Camstrup. One of the things that we want to talk to you about today is an innovative new solution for identifying leaks in your water mains using just water meters. So we're not talking about customer side leak detection, which is essentially just continuous flow through the meter. What we're actually talking about and going to be talking about today is how we can actually reduce NRW using acoustic leak detection in ultrasonic water meters, not only to identify leaks, but to continuously identify new leaks as they happen in order to keep your NRW low. Then we'll go through a case study, customer example of what they were able to do with the technology once they got it in their hands. So what types of water main leaks are we trying to identify? A hint, it's not this one. So what we're typically looking for when we're talking about water main leaks is unreported background leakage. So we're not trying to identify leaks that are bursting through the ground. I know when it comes to the news media and when you talk to people in the public, when they think of a water leak, that's what they think. They think of either pooling water, sinkholes, or geysers. We don't really need to worry about those because those get reported fairly quickly. They get repaired fairly quickly. And yes, they lose a lot of water in the short amount of time that they are erupting. But because they get repaired fairly quickly, they're not losing a ton of water into the ground for an extended period of time. We're also not going to be talking about background leakage, which would just be like seeps or weeps, like a drip every now and then. What we're actually talking about is leaks that are actually putting enough energy into the system to be detected acoustically, either right at the leak source above it or nearby. So when we talk about leak detection technologies and we talk about leak detection strategy, just about anything that you would use for leak detection is going to follow this same pattern. You're going to do a system assessment. You're going to try to localize, essentially narrow down your search area, send someone out to investigate and confirm and pinpoint if there's a leak on site, and then repair and report on it as far as your EPA guidelines and water loss reporting, as well as for your audits at the end of the year. So what types of acoustic leak detection survey technologies are out there? Most people are fairly familiar with ground mics, listening sticks, things like an elephant's foot with headphones, as well as lift and shift noise loggers, which I think you saw a little bit in the previous presentation. They also have the ability to do fixed-based noise loggers. So it would be any kind of a noise logger where we're attaching an endpoint to it, or it has cellular technology built into it. There's also in-pipe surveys, which are things like the smart ball, which are typically used on larger transmission mains. Then you have correlators and satellite leak detection. So correlators are just for kind of pinpointing, and satellite leak detection would be a top-down overview. So give you an idea of what we're talking about there, for the most part, is what we refer to as one-time leak survey tools. So your listening sticks, it's actually a person on the ground going out and listening to all the fittings and valves and hydrants in your system and trying to see if they can find any leaks. You have RF devices, so your drive-by type loggers, where it's a lift and shift sort of mentality. You have maybe 50 loggers, 20 loggers, 10 loggers, whatever it would be, and you're literally putting them from valve to valve or shifting them to different areas of the system over time to try to systematically sweep the system for leaks. And then again, leak noise correlator, that's typically what's used when you're pinpointing leaks, just to try to get narrowed down. This is for your tougher shots where you have a lot of noise in the area. They can help you narrow down exactly where to start your investigations. The satellite leak detection is great as far as identifying large areas where you have leakage or trying to focus your investigation. The only issue we really run into there is looking for residual chlorine. So in a lot of the northern US, it has a little bit of difficulty because we salt the roads. So anywhere the pipes are in the roads and you put salt down, it's going to look like there may be a leak there. Again, in-pipe survey technology, that's for your large diameter mains. And then you have in-pressure or in-meter pressure monitoring, which will allow you to quickly identify catastrophic leaks. It's great for verifying a hydraulic model, getting it started. Biggest issue that you have with monitoring inside of a meter instead of like a separate logger device is that the 0 point is going to drift continuously inside the meter because there's no way to re-zero it without opening it up to atmosphere. So when we're talking about a pressure sensor, typically what that is it's a piezoelectric resistor. So essentially it's a mechanical device, almost like a spring, and it gets weaker over time. And if it gets weaker, essentially what will happen is the point where it thinks your atmospheric zero is at is going to drift up or down. So unless you take it out of service to re-zero it or expose that sensor to atmosphere, you can't re-zero it to atmosphere. So eventually it's going to get out of conformance. With most data loggers, you're looking at a battery life of about 5 years. So every year or so you'd be visiting it. Every 6 months to a year or so you'd be visiting it to re-zero it. And then every 5 years, you're going to replace the battery and recalibrate the entire device. When it's in a meter, you don't really have that option because you'd have to physically visit each meter to do it. When we're talking about acoustic leak detection inside a meter, we're no longer talking about adding extra sensors to your network. We're not talking about adding extra hardware, extra collection infrastructure, extra data plans. It's essentially, it works on the same principle as every ultrasonic meter. So an ultrasonic meter is going to have two sensors in it that are passing an ultrasonic signal off of two reflectors. As water flows through the meter, the ultrasonic signal going with the direction of flow speeds up, and as it's going against the flow, it slows down. What we're doing is we're measuring that transit time. In order to do that effectively, we also have to account for all of the background acoustic interference that could affect our ability to hear the shift in that signal. So essentially what we're doing all the time, regardless, is we're listening for everything that's going on around that meter, whether or not there's flow going through the meter or not. So what types of leaks could you potentially identify with a meter that has this technology? Well, we know that leaks, when they burst, they're going to add extra energy in the form of sound to the water column, to that pipe wall, and it's going to transmit through that water column and along that pipe wall. With the ultrasonic meters, you're essentially listening through the water column. So you have the same type of performance as you would have with a hydrophone, except you don't have to cut in anything anymore. You don't have to add an extra tap. You don't have to get inside the water column because the meter is part of it. So that gives us a little bit extra range compared to a noise logger that would be sitting on, say, a valve or a hydrant. The other thing that's nice about that is when we're connected to the water column like that, if a leak is occurring on the service before the meter, we're going to know fairly easily that that is a service leak because it's going to tend to vibrate just that service or maybe an adjacent service nearby. The issue is that service line doesn't weigh very much. So when there's a leak on it, it doesn't transfer a ton of energy to the main line. When there's a main leak, it's going to vibrate every service that's connected to it. So when we have a mainline leak, pretty much every meter that's around it's going to light up and give you some sort of information as far as how loud it is in the area adjacent to that meter. And again, you're going to get the same kind of typical alarm codes that you would get for continuous consumption or burst codes, letting you know that there's excessive consumption going on beyond the meter, or whether or not there's any flow whatsoever. So this gives you the ability to tell before you roll a truck, is this likely to be a customer responsibility? Is this on the utility side? And it'll help you identify, is it on the utility side of the service, or is it on the water main? So why do we want to use acoustic leak detection inside a meter? Why are we looking at built-in embedded acoustic leak detection as opposed to adding external sensors? Well, one of the nice things with it, and a lot of the questions that we get when it comes to sensor technology, especially acoustic leak detection, is how far away can you hear the leak noise, from its source? And it's not really a question of how far we can hear. It's more a question of how far the noise can travel along that pipe wall or through that water column. And one thing that we have found is that noise travels further and faster through the water column than it does along the pipe wall. And the nice thing with that is if you're using poly services or using, say, HDPE mains, when you're listening through the water column, we don't have to worry about the pipe itself absorbing the energy of the sound. We can hear through the water, and it typically moves about as fast as it would move through, say, a ductile iron pipe that's 4 inches. So it's going to transmit the sound very well, very easily. One of the big things, though, is just reducing the complexity, reducing the cost. You don't have any extra hardware anymore. We're just using the sensors that are in the meter. We have an extra module in there to make sure that everything's quiet while we're listening, so that we're only hearing everything around the meter and not what the meter is doing or something that's going on when there's flow. But it gives you the ability to literally install a like-for-like replacement with the meter that's in the ground, and you don't have to attach a separate sensor. There's no extra wires. There's no extra endpoints. It's literally the meter itself, and everything is built in under the glass. For utility, what this really provides you with is the ability to cover every part of your system with acoustic leak detection. In the past, okay, like was mentioned before, I spent the last 10 years developing cellular acoustic leak detection and correlating monitoring devices. In the past, every time there was a leak detection deployment, what we were attempting to do is what's called a minimum viable survey deployment. Essentially, how few devices can I possibly put in the system and hopefully cover most of it? What that means is typically these sensors get spaced every 500 to 1,000 feet, sometimes 1,500 feet if your valves aren't close together. When it comes to installing a meter that has built-in leak detection, those meters are typically spaced, like in towns, 50 to 100 feet apart. So not only are we able to hear just as far, if not further, than most of the loggers that would be sitting on top of valves or on hydrants, but you have 5 to 10 times as many sensors of the system listening all the time. When it comes to acoustic leak detection software, all of them are going to be fairly similar that are on the market out there. You're essentially going to get an acoustic graph, so you're going to see what the noise level is in the background. You're going to see the change when a leak occurs, and when the leak is repaired, you're automatically going to see it go back to baseline. If it doesn't return to baseline, we know that it's more than one leak. So giving you a few examples, when we're talking about built-in leak detection, what we're really trying to do here is focus on analyzing how we handle the leaks. So we have so many sensors out there. One of the big concerns for most utilities is, okay, we're going to install these things and it's going to find all of our leaks. How are we going to deal with kind of managing that situation as far as how do we prioritize the most important leaks, the most critical infrastructure, and how are we managing our resources as far as man hours most effectively? So the nice thing with having it built in, again, it's acoustic leak detection across your entire network. You get 7,300 distribution-wide leak surveys over 20 years. The big thing when we're talking about how do we actually manage this, so most logger systems that are out there, or most data logging systems that are out there for leak detection, are going to essentially listen at 2 a.m. every day. And the reason they do that is because they're trying to do it during a period where hopefully most people are sleeping, so we don't have a lot of ambient environmental noise from people moving around. And hopefully, if you're asleep, you're not using water, so your tap should be shut and your pressure is going to be a little higher, and that'll make any existing leak scream just a little bit louder. So that's why they listen at 2 a.m. Big thing though is because they're trying to conserve battery. So battery life in most typical acoustic data logging applications is somewhere between 5 and 7 years. With a built-in meter, because we're constantly monitoring for the acoustic noise value around us anyways, in order to optimize our ultrasonic signal, there is no effect on battery life to be able to get all of your audio levels throughout your entire system. The other thing is, because there's no extra hardware or infrastructure, you don't have to have any extra manpower available to actually maintain a whole separate system just for leak detection. And because it's coming back over AMI, most utilities that are moving from AMR or a similar system can repurpose their meter readers to actually do leak detection full time. And we'll get into a case study example here in just a little bit where that's exactly what it did. But the kind of the big thing is no hardware costs, no infrastructure, no manpower, and you get 10 times as many sensors. They're listening every 55 minutes. So instead of once a day at 2 a.m., we listen every 55 minutes, which is 26 times a day, and we record the lowest value of the day. So if there's a leak, it should get louder and it should stay louder. It shouldn't go away. If it goes away, we know it's intermittent noise. It's not a leak. What we're really trying to figure out is there a way to get rid of other sources of noise within the system? Things like PRVs or pump stations, things that could generate a ton of noise that'll go a lot of times for blocks in every direction. So what we do is we're sampling all the time, every day, and we're recording the lowest value essentially when those pumps aren't running. So to get into a case study testimonial, I'll give you an example of kind of what this can do and how it can actually help you reduce your water loss and then keep it low. We have the town of Oneida in Tennessee. They had 4,620 AMI ALD meters installed. So they did an aggressive change out. They only needed 15 collectors to cover 118 square miles, 322 miles of main line. And they wanted to do it in a 6-month deployment. So again, they changed out their 4,620 meters. And the reason they wanted to accelerate it in a 6-month kind of change out program was that their water loss was at 51%. So when they first came to us, they were at 51%. Within the first 3 months of having deployed the meters, they went from 51% water loss down to 28%. Of that, 10.7% was just from the initial changeout, which is fairly typical. The meters that we have not only have the lowest failure rate in the industry, they also have the lowest starting flow capture rate in the industry, which means all of that flow that can go through a meter before it actually starts spinning at a quarter of a gallon a minute, all of that gets captured in here. So as it gets more inaccurate, we're talking typically 5% just from going from a mechanical meter to ultrasonic. But after 5 years, that accuracy starts to degrade just based on your water quality and other environmental factors. How much is being used, how much is not being used, things like that. But typically we'll see a recovery of somewhere between 7 and 13% just on the low flow capture that we've been missing with mechanical meters. But when they initially started up, Oneida had 77 meters that had acoustic noise level over a value of 100, indicating a potential leak. They initiated an aggressive water loss recovery program. They took their 2 full-time meter reading employees and they retrained them to become full-time leak detection employees. So they were trained on how to use ground mics, correlators, and they went out and actually started finding the leaks or locating the leaks and repairing the leaks that they found with the system. Using the ALD equipment, the ALD meters, they were able to repair more than 70 leaks in that first year, which was 2022. And now 2024, they're expected to be below 15% water loss. I believe the last I heard they were around 14%. So that's going to save them approximately $140,000, and it'll gain 36 working days not having to go out and read meters anymore. Give you an example of some of the types of leaks that they found. So they did find quite a few service leaks. Most of them were before the meter. The types of leaks that they're finding, so anywhere from something like this, where it's 2 gallons a minute, it had run for 5 months by the time they got to it, because again, they had 70 some leaks that they were trying to get to. It was a ductile iron main. It's only 30 feet to the actual meter from the main line, and it's 150 feet from there over to where the leak was. But another example, this is a 4 gallon per minute leak. It had been running for 4 months by the time they had gotten to it. So they saw the spike on the graph. They saw it was increasing. By the time they got to it, it had been 4 months. In that time, this leak had lost 777,600 gallons of water just before the meter. And prior to having this system, they would not have known about it because it wasn't large enough for the homeowner to notice a reduction in pressure, but it was large enough to go down a stream and down a hill and into a creek and be completely filtered, not show up when they did their chlorination test. They wouldn't have found it without the system, essentially. But during that initial change out, United Water Treatment Plant was operating around 15 hours a day. As a result of the reductions from actually going out, repairing their leaks, finding their leaks with the system, their water treatment plant operating hours are now down to 11 hours per day. And fun fact there, that equates out to 60 days, 60 operating days total per year. So they're now running their water treatment plant 2 months less per year within the first 3 months of having changed out their meters and started repairing their leaks. A few other examples of what's typical, what you'll find out there as far as leaks. So this is a 180 gallon per minute leak that was found, repaired, wasn't surfacing, had nice well-drained soils and a very deep canyon here and a river right next to it here in Oregon. 6-inch AC main, the furthest meter away from it that was hearing the leak was 1,500 feet away. And a day after they repaired the leak, they saw a new leak occur on the furthest meter down that was hearing this initial leak. And that is very typical of what you'll find when you go out there and start actually doing leak detection in your system. If you've been in the past, if you've been sweeping your system systematically, maybe you do a half the system a year, a quarter of the system a year, whatever it be, you're going out there manually surveying it. You repair all those leaks, and typically the stories I've heard is we've repaired all the leaks and we saw the outflows from the treatment plant go down for a few days, and now we're right back to where we were before we repaired anything, and it just feels like we're kind of chasing a dragon that we're never going to catch. Having built-in acoustic monitoring throughout your entire system means that you can repair those leaks, and as soon as a new leak occurs, you're not only being notified, but you're able to see it instantly in that same area. You're able to actually tighten up that zone, tighten up that part of your system and keep it tight. And because of that, your NRW reduction goes from an imaginary number to a concrete number, and you can actually keep it low and drive it lower. Here's another example, also from Oregon. It was a 14-inch main, 30 gallon per minute leak. Distance heard was up to a half a mile on both ends. So this particular main had galvanized service connections, which means that it transferred sound from the main and from that water line very well without losing anything. And we were able to hear it up to a half a mile away with the sensors just in the meters. And then a couple of other examples. This is Madison County, Alabama, where they've installed their meters. This leak had been running for 2 months. It equated to 432,000 gallons in lost water. And it had been running for 12 months. It would have been over 2.5 million gallons of lost water. Now it's only estimated at 5 gallons per minute, and it was only running for 2 months by the time they had gotten there. But it was a utility service line made from polyethylene. And they've had loggers in their system, like on valves, on hydrants. They've had people going around sweeping it before. The issue with polyethylene service lines is that it doesn't transfer the energy to the main nearly as well as it does to the meter that's attached to it, just because that service line doesn't weigh very much, so it's not shaking that main. If the leak had been on the main, it would shake every service around it, so every meter would hear it. But using loggers, this is something that they weren't able to find just because it didn't transfer enough energy to the main to light up the loggers. And then Ephrata, Pennsylvania, this is a mainline leak that was found before it surfaced. And again, this would be typically fairly easy to find, even if you were out there with a listening stick, just ground miking the ground or on the road as you're going past. The issue is that in the past, that's what they were doing, and they were sweeping their system like 1/3 of their system per year. So even if they had found a leak nearby, when this leak popped off a week later, they probably wouldn't have gotten back to this area for another 3 years because this leak never surfaced. So it was leaking at a 12-inch main. It was leaking from a clamp. It was only 55 feet from a copper service line. obviously we can hear it very well. Any loggers would be able to hear that very well. But if you're sweeping your system, it's something that you're only going to hear it when you're standing right there. And that's kind of the benefit of having the built-in monitor. You don't have any of the kind of the overhead of manually going around sweeping anything. You're able to keep on top of new leaks as they occur and repair them as they occur. And you can actually reduce your NRW and then reduce your treatment plant runtime. And because you're also gathering all of that low flow capture that you don't have before, it's additional revenue to the wastewater side as well. That's it for me. Anyone have any questions?
All right. Thank you very much to Graham and David for those presentations. If you do want to reach out to them for more information, their contact information is on the screen. I'll leave that up as we go through the Q&A here. There was a question that came in at the end of, or just before Dave's presentation, about calibration frequencies, replacement frequencies. Are there software updates for these AMI structures? Just some details about kind of the admin side.
Yeah, I can take that one. So from certainly on the AMI side, when the systems are deployed and they're out there, the equipment itself, I mean, it can go years with, having to be serviced or any that portion of it. From the inside of the utility, when you talk about applications and those things, when on a hosted platform or a cloud platform, those updates usually, they're going to occur. A major one's usually going to be at least once a year, but the utility is always notified, and there's test servers set up for that type of procedures that allow them to test out everything before it actually cuts over to the new version. So hopefully, Sean, that helps answer a little bit of the question there, if not all.
We'll see if any follow-up questions come in. But yeah, I think that'll work for now. Yes, we will have this presentation available. We'll upload it to our website you can review the recording, and we'll also have a PDF of all the slides. So Graham and David both supplied their presentations to me. So we'll have that all uploaded to our website. Another follow-up question on the AMI side for cities considering that maybe don't have it implemented yet. The types of signal and control systems for AMI. I know there's cellular, there's radio. Are there pros and cons of those different options?
Well, there certainly can be. We always prefer on the census side that we use a licensed frequency from the FCC, because it's if it gets interfered with, obviously we have rights to be able to get that under control. On a cellular side, the one thing with, as we know, cellular side, they can change technologies sometimes, fairly frequently. So that means you might be under a 4G, 5G system, but you don't necessarily know if your technology is going to be compatible with that. And also the backwards compatibility is another advantage of certainly, the AMI side of, using, say a licensed type of frequency.
So I can speak to that as well. So we also use a licensed frequency for our RF side of things for our AMI systems. We also have cellular meters, but we've gone with the NB-IoT network, which is a M2M dedicated network specifically for machine-to-machine devices. So it's dedicated for devices like a meter, where it's not passing a ton of data, but you need long battery life and extremely long distance communication. So it has about 3 times the range of like a typical cell phone would for the cell tower, because we don't have to worry about it carrying video or something like that back across the network. But they've actually gone out and dedicated that spectrum specifically for this, and it's expected to not go away for the next 25 years. As far as 2G, 3G, 4G, I went through that entire transition on a product development side. So yes, I totally agree with that statement. As the technology came out before the networks were really ready for it. I took a bunch of equipment through the process with Verizon and had to teach them how to test the equipment because they weren't expecting to have hundreds of thousands of devices passing tiny amounts of data on their network. So When it comes to NB-IoT, it works great. It goes through structures really well. It goes through dirt, water, even cast iron lids really well. You don't have to replace lids hardly at all with them. It works pretty slick. The biggest disadvantage with it is you are paying monthly for that, connectivity charge. It's not very expensive, but it's more than nothing. And when you have an RF system in place, you're essentially paying nothing for the communication.
We had another question come in here about how, for both of your systems, how do they play with pre-existing systems? Do they have their own separate billing structure, or are they able to integrate into pre-existing AMI billing structures?
Yeah, I mean, from our side, certainly we integrate with all billing systems. We have a professional services group, and what they're able to do, they already have contacts into basically all the billing, companies that exist out there. So they already set up all the files. Everything integrates usually very, very smoothly and quite nicely.
Yeah, it's the same deal. It's a very simple process, and we've integrated with almost every billing manufacturer that's out there. So the systems typically are already in place. We're just literally matching the way that you're sending the data in currently.
Can you speak a bit to funding structures and how projects get implemented? Do you see batch processes working through grant applications? Do you see any like public-private partnerships to like a performance contract to swap out meters, things like that can help communities?
Yeah, I mean, we do. On our side, mostly what we see is, utilities that start to look and try to look at the government grants and, get those implemented, get those in place, and then they utilize, funding from that to, pay out, their smart AMI deployment, for that side because, there's always, the state grants, there's the federal grants. So that's usually the way that we see a lot of it go. I've seen a few partnerships that happen in some of the communities, but generally it's more rare for me to see that occur.
Yeah, we've seen quite a bit of different, all the traditional funding sources. You have your grants and your loans and bonding and everything like that. Recently, in the past couple of years, though, we had a company reach out to us and partner with us called Sustainability Partners, where they literally go out and they provide meters and network as a service. So they not only do they do all the maintenance and everything for you as far as maintaining the network, anything that goes wrong with the meters get replaced by them, as part of the service. But they also have a kind of an innovative way that they can help you fund these types of projects. Essentially, unlike a performance contract where a lot of times you end up paying double, and if it doesn't work, you kind of get half back, which isn't a great business model on the utility side. What these guys are actually doing is they're essentially charging like a usage fee per meter per month. And instead of having to raise your water rates in order to finance the system, they're essentially saying, okay, well, just tack on a service fee of say $5-6 a month per meter. And then the warranties are extended in perpetuity, which means that your meter never goes out of warranty. It's just replaced automatically forever if anything goes wrong with it. And they only are worried about seeing a payback by year 12, because as long as they can see a payback by year 12, that fulfills their bonding requirements, basically what they're funding. So they're going out and selling bonds based on these basically contracts that they're doing. And that's funding things like school retirement pension funds, things like that. They're essentially investing in these as secure investment vehicles. So they're looking at 25 years down the road, as long as the bond requirements are fulfilled, great. And from a utility standpoint, the utility doesn't have to put up anything up front. They don't have to increase their water rates. They don't have to go for bonding, try to get loans, things like that. It's been really helpful for a lot of larger utilities that have been cash strapped, a lot of utilities where they have aging infrastructure and they just don't have the money to get it done. Essentially, the philosophy is a lot of these utilities are trying to get out of the business of repairing and maintaining meters and a meter reading system. So essentially, this company, Sustainability Partners, comes in, they purchase all the meters for you, all the infrastructure for you, install it, maintain it, and The only time they get paid is as long as that meter reads. So if the meters don't read, they don't get paid.
Interesting.
And I think that their business model is based on meters failure rate of 7% or less. Ours is right around 0.25%. Historically since 1993. So because of that, they have extreme confidence to be able to go forward with us and say that this is a sustainable model for the future. We've had, I think, 7 utilities in the last month that have purchased systems through them or finance systems through them in order to get stuff in the ground.
We're coming up at the end of our time here. I got one last question, just to help communities with planning and things. Are there any things you see where they're commonly overlooked things as people are planning an AMI conversion or upgrade? You're muted, Dave.
Yes, one thing that I do see is when they start to investigate for, you know, an upgrade into an AMI system, it actually just came up in a question previously about the billing, right? We see that, you know, sometimes the utilities aren't going back to their billing companies and saying, hey, we are going to be moving to this model, and we really need to you know, make sure everything's going to consistently work. So sometimes we see there's a gap that occurs when, you know, they don't talk to their billing company, and now all of a sudden this data's, you know, becoming available, and the billing company's got to make the transitions to help the utility. So we always say, reach out to your billing company whenever you're fixing to make that determination or to go to, you know, an AMI system.
And from our standpoint, we always tell our customers to first and foremost focus on the meter. Make sure that the meter that you're putting in is a quality meter that you're not going to have issues with, and make sure that the type of infrastructure you're putting in to collect that meter reading is applicable or good in your topology. So typically, if you have a license frequency, that's going to help eliminate a lot of concerns with range and other things breaking down the frequency. It's a question of, you know, are we going to get a meter that's going to give us quality and accuracy over 20 years and a battery life that actually meets 20 years? And then from that point on, it's kind of deciding what else can we do. But make sure you start with a good foundation. That's our philosophy on it.
All right. Well, thank you both for the informative sessions today. Again, if you have any questions for Graham or David, their contact information is on the screen there. Feel free to reach out to them for more details. Also, if you're interested in one of our no-cost assessments, please do reach out to CDAC at our website, smartenergy.illinois.edu, or email me. I'll get that up on the screen there. And let us know if you're interested. Again, we've only got a few slots left for this program year. We wrap up our program at the end of June. So if you're interested in one of those assessments, please do reach out to us as soon as possible. Graham and Dave, thank you again, and I hope everyone has a wonderful afternoon.